Good morning, everyone. Since people are still joining, we will very slowly ramp up. Good to see you all. This is actually the first EuroCC branded training which we organize, so purely EuroCC branded. And we actually have a guest lecturer today, and I'll ask him to introduce himself a little bit. But I've known him for quite a while, because he used to be a user on our VSC infrastructure, and he has already given a talk for the VSC, the Flemish Supercomputing Center, a couple of years ago, and that was specifically on GPU computing. So now today he's going to talk about performance-aware C++ programming, and Vukasin, I'm going to give you the word. You can also take over the screen, and the floor is yours.
Hello, everyone. Can you guys hear me clearly?
That seems to be okay.
Okay, great. Thank you. Thank you, Gert. Hi. So yes, thank you for the introduction. So my name is Vukasin. I have collaborated before with the Vlaamse Supercomputing Center, and I've known Gert for quite a while. In fact, I did my PhD here at KU Leuven, but on GPUs and performance optimizations. And since then, I've taken quite an interest in optimization in general, and I'm happy a lot of people have decided to join us. It means that it's an interesting topic. I will get into this in detail later, but there are certainly many applications in academia and in the industry that can benefit from performance optimization. And as you will see throughout the talk, some of these performance optimizations don't require a lot of effort, and some do. So the goal of the presentation here is going to be to give you kind of a tool set that you can try to pick and choose from, and increase the speed of your code accordingly. So let's get started right off the bat. So the name of the talk is Performance-Aware C++ Programming. So I'm happy to see also that so many people are interested in C++. It's certainly a language that allows us to delve in deeper. It's a systems level language, so it gives you the tools to do sort of micromanagement of memory if you so choose. And as we'll see throughout the talk, really managing memory is the number one, just like with GPUs, is the number one consideration in terms of performance. I have to mention one thing up front. So 2 days ago, I managed to catch a cold, and I'm still recovering. So if you'll have to excuse me if I have to pause for a few seconds just to get myself back up and running. It's a long talk as well, so it's 2.5 hours, and I plan on doing one or two, probably two short breaks in the meantime, so we can all have a glass of water or whatever. Aside from that, I hope you find it interesting. I think it's the presentation is approachable to everyone, because I'm sure we have quite a range of people here with more or less experience, and the idea is to be able to explain and maybe show is a better word, something interesting to everyone. So let's get started. So what you will hear about is, of course, the introduction and a few slides, something about the hardware, because without really having some understanding of the hardware that your code is running on, there's not a lot to talk about in terms of performance. So you have to know what your hardware can do and what you have inside the machine that you are running the code on. You don't have to have perfect knowledge, but some intuition is very, very useful. Something about data structures and how data structures affect performance. They have a profound effect on how fast your code will run. Then vectorization and multi-threading. Here we'll talk about, oh, I'm sorry, am I not sharing the slide? Apologies. Yeah, thank you. Thank you for bringing that up. I just noticed. Can you see the slide now? In a second or two. Yeah. Okay. Sorry about that. So the vectorization and multi-threading, we are not going to be doing any kind of manual vectorization, which you can do using intrinsics in any compiler. or manual multi-threading. This is going to be about how the compiler handles auto-vectorization and auto-parallelization. Then we're going to slow down a little bit and talk about the compiler. The compiler can be your friend and your enemy at the same time, and it can do wonders in terms of performance, but there is always a few quirks, and the world of compilers and how they operate can be very esoteric and unintuitive. So it's always useful to see things from the compiler's perspective. And then we're going to wrap it up with a use case of phase unwrapping. I'll explain what kind of algorithm this is, where it's used briefly, and explain what it does and how we can make it faster. And then, of course, throughout, I'm going to show you some examples and timings and what change brings about what kind of speed up. So first of all, why do optimization? Why, in general, it's a very expensive thing to do. It takes a lot of engineering time. It takes resources, and frankly, the world of software is so wide that there's plenty of use cases where the speed of software is just not worth it. I don't like that perspective personally, but when I started learning programming, for us, it was number one, does the program provide the correct answer? And number two, how efficient it is. And it was always very, very highly valued if your code is faster and if it consumes less memory. So those are kind of the two very basic measures: space and time complexity of your code. And there are many areas where this is very, very important. So for example, academic numerical simulation, for example, in general, numerical simulation in the industry, it certainly pays if the program runs shorter and provides the same result. AWS or other cloud services, you pay less if your program runs faster. Anything to do with mobile technologies and the attention span of a modern user or web can be very short, and people lose patience if the applications are not responsive. So there's a direct link to the customer in that way. So plenty of use cases of why optimization is important. And still, if I take a look at, for example, I don't know if you share this opinion, but if I take a look at some of the applications that I use on a daily basis, like Visual Studio or Word, I find that they are even slower than they were 10 years ago. So, and the advancement of CPUs and in general computing technology has risen so much, and we have such powerful computers that I really struggle to find sometimes the justification of why it takes 4 or 5 seconds to load up Word on a machine that is maybe 50 times faster than it was 10 years ago. Same thing goes for Visual Studio, Teams. For Teams, maybe you can make the case that it has a lot of networking, so there's an inherent latency there. But many other applications that are user-facing have become slower. Why is that? And perhaps it's because we've simply changed our priorities. I don't know. But the fact is, computers are cheap and fast. They really have gotten cheap and incredibly fast, and it simply perhaps pays not to invest additional resources into making an application faster, especially for applications that are, let's say, monopolistic in some sense, very large applications that people use when you don't have a choice. Perhaps it doesn't pay to put money and resources into making it fast. So for the first part of the talk, the language that we're going to be using doesn't really matter, especially in terms of hardware. If the language is a systems level language such as C, C++, Rust, the rules in this section and in the following section are going to be pretty much the same. And the talk is structured such that I try to go from fundamentals of performance optimization down to some niche topics, but that doesn't necessarily mean that the niche topics have a smaller impact on performance, or that the fundamental topics have a higher impact on performance. Loosely, it is true, but not always. And I'll show a few examples where really small, tiny changes to code or how assembly is generated can increase the performance dramatically. And again, I repeat, optimization is a very broad topic, and I'm not here to give all details on all approaches, but rather to provide you with a general overview so that if you have codes that you are maintaining or building, you could have a tool bag that you can just reach for and say, maybe data structures are wrong, maybe the assembly is being generated incorrectly, maybe I should buy an SSD or things like this. So it's meant to give a broad view. However, we will have to go into some detail briefly in a few spots. So first, let's ask ourselves whether we are solving the right problem. If you know you understand your problem, say you're writing a finite element analysis tool and you're an engineer, are you using the right algorithm? So this talk won't help you with that. That's impossible. That's up to you really. If you're solving the wrong thing, no amount of optimization will help. And is there anything about the problem that is general but doesn't need to be? It's a typical question that I ask myself when I'm developing code. And to give you an example of that, so in terms of whether we're actually solving and optimizing the right problem, I'll give you an example. Normally, when we write code, when I write code, I typically have a ground truth prototype written in MATLAB or in Python that can work in double precision and I know is correct. And then I work up from that into C++ and then an optimal version of it. However, many algorithms that are already done, and let's take an image convolution, for example, they are written in a very general sense that these higher level languages like Python or MATLAB or Julia provide. Say if you're doing some kind of image convolution with a certain kernel size and you want to blur or whatever, normally these languages provide very, very general, say, convolution functions. And does your program actually require it to be general? So what you're implementing, if you reduce your problem to what you actually need, it can bring about large speedups. For example, you know that your kernel size is going to be only 3 by 3, and you know you're going to be using only single precision, and you don't need double precision. There are ways where you can use that knowledge and discard the rest, which will make your code faster. So, for example, you have more cache space to play with if you're using only single precision. So that's a very important thing. What am I developing? Have I chosen the right algorithm? And does it need to be general? If you remove much of the generality, what you're left with is only what you need, and then you have more freedom to optimize. Same story with PCs and computer gaming consoles. Gaming consoles don't need to, or developers don't need to build code that can work on any hardware, on any PC configuration. They have a set hardware, and they can therefore optimize much better. So why is a program slow? So there's many answers to this, but I think the best one that I could come up with, it's either doing unnecessary things or is just waiting for data. So if your program is slow, and if you open Task Manager or whatever you want to use in Linux and you see that the CPU is not at 100%, then you know, if it is at 100%, you know you're utilizing the machine. If it's not, that means that the CPU is waiting for something to execute your instructions. When we say if the CPU is constantly pumping out math, so constantly adding, multiplying, dividing, whatever, then you're doing a good job. If it's waiting for data, waiting for the operands of these operations to arrive for too long, then it's starved for data, and you will see lower utilization, which means that you're actually wasting that time. But we'll get to a little bit more detail about that later. So minimizing this waiting time is most of the presentation. Algorithmic improvement can only be addressed briefly because they are so situation specific. It's very hard to make some kind of, general, come up with some general advice that will work for everyone. Let's talk about hardware a little bit. So computers are extremely fast, but it's easy to get fooled to think that they're not. And that's one of the reasons is because I think we've been conditioned by so many web apps where there's inherent latency in the response time, and then we don't care when we see a desktop application that is sluggish. In fact, an application that is written for the desktop, unless it's running some serious stuff in the background, really has no excuse in being sluggish, especially if we're talking about GUI. Another an important piece of reality is that advancement in computing hardware, so actual computing hardware like CPUs, is much, much faster than memory hardware. So if you look at back 10 years, you will see that the number of floating point operations per second that you can achieve with a modern CPU is maybe 50 times what it was 10 years ago. But the speed at which you can get data from RAM, random access memory, has not increased nearly as much, maybe 2 or 3 times, or maybe I'm underselling it a bit. So there's a discrepancy here that we have to take into consideration. And by the way, this is why caches exist. There's generally discrepancy between different parts of the computer and how fast that they can work. At a high level, for a computer to perform an operation, it needs several things. So it needs a free port, what we call a port on the CPU to perform an operation. So it needs an adder unit available to add. Say you want to add two numbers. It needs the actual instruction. So it needs to know that that's the operation that it needs to do. And it needs one or two operands, say 2 operands, and those are normally in RAM as well as the instructions. When your program loads, things go into RAM, the operands and the instructions have to be there, and then they come closer to the CPU. If the CPU doesn't have any of these 3 things, no port to do the actual computation, no instruction telling it what to do, or no operands on which to perform the operation, it waits. Now, other things can happen. Another thread could jump in, switch the context, and run its own thing. But in general, you want to be able to feed the CPU with as much data and as much instructions as you can. Otherwise, it's waiting and wasting time. So let's see how well we can do that. This is a very simple illustration of the von Neumann computer. And so a disk, CPU, RAM, and I've put in here a GPU. And the speeds at which memory can be retrieved and the links over which the memory has to flow. So disk, the amount of data you can get out of the disk, say you're writing a program that has to read stuff off the hard drive and churn the data. Let's say you're training a neural network, right? There is a physical limit on how fast you can actually do this. So for example, you have a neural network and you have 1 million images on your hard disk, and your neural network throughput is let's say 500 megabytes a second. You have a powerful GPU. You can train the network with a lot more data, but the disk can provide you, if it's a hard disk, can provide you only with 200 megabytes. So obviously this is your bottleneck, and it's the first thing you want to perhaps take a look at, and just replace it with an SSD that has a much higher throughput. 3 gigabytes per second SSD and 200 megabytes here are actually sequential read speeds, not random read speeds, and neural networks require more random read speeds, but okay. Then the link between the disk and RAM, that's the PCIe bus of your motherboard. So you have to take that into consideration as well. In terms of disk, it's not that important, but you share the PCIe bus and you might not have sufficient lanes there to work with. RAM in itself, the technology, the physical technology also has certain limits on how fast it can provide you with data. This is a large number, 80 gigabytes per second, but and for most CPUs, this is more than sufficient. But if you take a look at the internals of a GPU, GPUs can provide more than a terabyte or around a terabyte of data to the computational core. So it's a 10-fold speed up. And then you of course have a link between the GPU and the RAM. How fast? Say you're training on a GPU, right? And the data typically passes through RAM if we don't take into consideration other technologies. So you have to think about whether the link between the CPU and the GPU, between RAM and GPU has a sufficient bandwidth. And then the link between the CPU and RAM is at around 100 gigabytes per second. And you'll notice also the yellow squares. These are caches. They are here to sort of alleviate this difference in speeds at which, say, a CPU can consume the data and RAM can provide the data, or the disk can provide the data and the link can give it to RAM. I don't know if you've ever noticed, let's say you're writing down to a file very quickly at a very high rate. You're writing down to a file and you're expecting the data in a certain file to be flushed to the hard drive at all times, which is not typically what a person would do, except when you say it explicitly. But if you want to work with a single file at a very high frequency, normally it is not a good idea. But if you actually try it and time it, you'll see that that you get a throughput that's much bigger than 200 megabytes a second, and that's because of the cache. So the file that you're saving to the hard drive doesn't actually exist physically because of the cache until either the operating system tells it to store or the controller on the disk tells it to store physically. So it's kind of a buffer between the technology and yourself or the CPU. Very, very important. And let's take another quick look, and I'm going to have to hurry up with this one about what the internals of a CPU look like. So for those of you that are unaware, normally when you start a program, everything about that program loads into RAM. And what you would want to do is also load the data that you want to use, say from a hard disk, into RAM as well, so that it's closer to the CPU, uses the high bandwidth interconnect, and uses the RAM technology to provide you with data faster. But once you request a certain operand, let's say from RAM, it has to go into the GPU for you to compute with it. In fact, it has to go into the registers of the core that is tasked to perform this operation. And as it does that, the assembly operation gets issued. Something goes into RAM, grabs the data. In fact, it grabs 64 bytes around the data that you want, which is one cache line, and goes over the interconnect, leaves a copy in L3, leaves a copy in L2. It already knows where to go, leaves a copy in L1, and ends up in the registers. So that next time that you want to use the same variable, the machine is not going to go back to RAM to pick up your data. It's going to check whether that data is still in L1. If yes, it'll use it. If it's in L2, okay, perfect, it's going to use it. If not, maybe it's in L3, and L3 is shared, so perhaps a bigger chance that it'll get evicted by other processes. So you see this very useful buffer that is happening between you and RAM. We want to avoid as much as possible having to go back to RAM to get the operands that the CPU needs, because it's very expensive. And just how expensive it is, you can see here in the third column, latency. So L1 cache hit is 1 nanoseconds, L2 cache hit 4 nanoseconds, then 40 L3, and 120 nanoseconds is, these numbers are approximate for relatively modern hardware. They do change slightly from generation to generation, but this is the order of magnitude. So you don't want to pay 120 times more for a fetching of one cache line from RAM unless you really have to. And in here, throughput is really not what we are looking at. We're looking morely at, bandwidth is not what we are typically looking at. We're looking at latencies at this point. So more cache is better, right? And modern CPUs have a large amount of cache. So just to give you a quick example of an Intel CPU on the left, relatively modern 13th generation CPU. I think it's a 13900K, and a Ryzen 9. This is the latest, I think, consumer grade CPU that they have, 16 cores. So the amount of L1 cache for data, L1 cache for instructions in the bottom right, the L2 cache, 16 megabytes, and 96 megabytes of L3 cache. That's quite a lot of cache. So this table I'm also going to go by very quickly because it contains a lot of information, and we're gonna be strapped for time if I do this slow. So if you want to write performance optimal code or performance oriented code, it's very useful to have a general idea of which operations you issue take which amount of time beforehand, so that you can, again, develop an intuition of what you want to do often and what you definitely don't want to do often. So, and before that, you should typically have an idea of what the hot code in your code is, the hot loop. So in games, that would be the main game loop or whatever, the physics loop, something that is running very often and that is performance sensitive. And in there, of course, you want to avoid doing unnecessary things. For example, you would like to avoid opening and closing a file, because that's a system call that has a certain overhead. And you definitely want to avoid writing down to a file or forcing the writing of that file that in a hot loop, because everything else stalls. So we're going to go in chunks here. L1, L2, and L3 you've already seen. This is the order of magnitude that you can expect. from half nanosecond to around 10 nanoseconds. And interestingly, so in the range of 10 to 100 nanoseconds. By the way, this is before I proceed. This is not mine, of course. This is a modernization of a very famous post by a guy called Peter Norvig, and in a I think a Google newsletter post about latencies all programmers should know. I just found a bit more modern numbers because this is 15 years old. So L1, L2, L3 cache, extremely fast access. RAM access fast, but much slower, an order of magnitude slower than the caches. Something interesting to note, for example, in the range 10 to 100 nanoseconds, mutex lock-unlock exists. So to me, that says extremely, extremely fast. So if you have multi-threaded code and you are worried that frequent locking and unlocking of mutexes are going to become an issue, they probably won't, unless the execution time of your hot code is 1 millisecond or something. Typically, mutex lock unlock is free. Is free for most of the applications I've written software for. Context switching 1 to 10 microseconds. To me, at least in Linux, without switching out data, to me that says very, very free. Still, I'm not in the range that would worry me, and I will happily run 10 threads for a certain problem and not worry about the fact that they will have to switch out. Say if one thread is starved for data, do a context switch, another thread starts running. The creation of threads in Linux, I'm pretty sure it's a very similar number in Windows, is in the range of 10 to 100 microseconds. So perhaps architecturally, if you're thinking about how you're going to build your program, you might want to, for example, evaluate whether you want to do some kind of elaborate thread pool, start 10 threads at the beginning of your code and have them wait and then feed them data, maybe in a round robin fashion or whatever, priority queues or whatever. That requires a certain amount of skill in programming, or you could take a different route and just spawn a thread whenever you want it, especially whenever you need it, especially if you have a lot of work to be done with that thread, and that would offset then the time to actually spawn the thread. In C++, I believe it's std async that will do that. So you have some work you need to do. You don't want to bother making, producing consumer patterns or whatever. You can just use std async, name a function call, and it'll do that, creating a new thread from scratch. Or maybe it manages a thread pool in the background. You don't need to know this. But the point is, it's extremely cheap for many applications. And now we go into physically limited things, much more physically limited things. So reading 4K random read on an SSD, hard disk seek 5 to 10 milliseconds. So if you're writing to 2 files or 3 files that are in different positions on the hard drive, you might want to not have the seek head, the head of the the hard drive flopping back and forth between the 2 or 3 files, because you'll pay 5 to 10 milliseconds only for the seeking action. Of course, taking into consideration the cache, the computer should be, or the disk should be smart enough to mitigate this issue, but still, it's not good practice. And then we are in kind of the last 3 parts of this pyramid, 10 milliseconds to 1 second. We are in networking. And here, all bets are off, right? You have really very little control over where your packets go, how they go. The distance, maybe where they travel to and come back is a different story. But this is a few orders of magnitude more than what we will be dealing with in this talk. So overall, the pyramid of latencies, of course, starts with very tiny things, a CPU, very low latencies, then RAM, kernel, syscalls, very fast, but still something. Storage, very slow to interact with. Try to put your data in RAM and perform storage perhaps in a separate thread if you need, so that it doesn't block anything in the same thread, etc. And networking, also probably throw it in a separate thread and have a queue handoff data. Okay, 30 minutes. Okay, let's get into the fundamentals. And okay, maybe if you have some questions up until now, I could take a look. If not, I will continue. I hope it's not too fast. I will kind of have to be a little bit fast here. I hope it's interesting. Performance optimization in what sense? in the sense of yeah, how fast can you get a certain algorithm to function? And so I'm reading a question here from Oscar. Performance optimization in what sense? In the sense, can I get the machine to do what I want as fast as possible? I know a lot about my algorithm. I've chosen the right algorithm. I know my machine. I can apply some common sense. I've seen the latencies of the operations I will be running. How do I still get this thing to run as fast as possible for whichever purpose? Perhaps you're doing numerical optimization, right? Mathematical numerical optimization, and in your case, in a certain amount of time, you could run three or four analyses, and maybe two of these end up in a local minimum, and the fourth one finds the global maximum because you started with like four sets of different kind of parameters, and they all go their different ways. So that's one example of how can a 4 times speed up benefit me. Or you can do some kind of voting or whatever, you transfer it to a GPU. There's a lot to talk about in terms of how it can be used. But in what sense do I mean optimization? I mean, yeah, how do I optimize a certain certain code to run as fast as possible? So yeah, no problem. So let's go through the fundamentals. So I intend to go through this quickly and never come back to it again, I hope. One, avoid unnecessary work, right? So that's a no-brainer. Using the right containers. So most probably your application will use some type of container to store the data over which you will probably iterate. And if you don't have the fundamental or the basic knowledge of containers, really nothing will help you. There's no advice I can give you or anybody. So know what lists are good for, what vectors are good for, what maps and sets and decks are good for. I would say, if in doubt, use vectors. They are contiguous memory storage, so every element is right next to each other. You use caching fully this way. So use the right container. Use the right algorithms, I mentioned this before, and use the right data structure. So I have this whole section is about how to optimize data structures to get the most out of the computer. Try not to do new and free or a new and delete and or malloc and free if you're doing C in hot code, because the amount of time that it takes the machine to provide you with a pointer, well, after it has allocated memory, to provide you with a pointer that has, I don't know, 256 megabytes in it, is not deterministic, right? So as the machine continues running, you could get some memory fragmentation issues. It will get longer and longer for the machine to provide you with the memory that you asked for, especially if you are, especially if you are asking for data memory regions that are very different and have very different lifestyles. Lifetimes. So try to allocate all the memory you think you will need a priori, and then just dole out that information, those pointers, back to parts of the program that need it. Or if it's difficult, you can try using the stack instead of the heap if your data needs are much smaller. So there's a fixed amount you can use on the stack. Then avoiding unnecessary copies. Yeah, this is not extremely important, but it can get important. So if you have 256 or 200 megabyte image and you make 10 copies of it before you're done processing with it, it's not good, because you will have to, for every copy, do another allocation. So the new operator or the malloc function call happens automatically. And one good way to do that is to just add move constructors, right? So or move assignment operators. Since C++ 11, I think, moving in and out of the move assignment operators are a thing in C++, and they're very useful, so that copies are avoided. In fact, using newer versions of C++ makes that even better. So starting with C++ 17, there is such a thing as guaranteed copy elision in some situation. Copy elision means essentially copy avoidance. Say you are, say you have a function that has to return some kind of random distribution. A vector full of integer numbers that is 10 millions long, and you want this function to return it. You can declare this vector of 10 million numbers. You can fill it in and just say return vector. You don't need to think about the fact that it used to actually copy the vector out and then put it in a new location outside of that function from the call site. In fact, in the new versions of C++, that copy is completely elided, and provided some small conditions are fulfilled, you can look that up on CPP reference, the new object is going to be created in place already outside of your function. You can think of it that way. So using new versions of C++ is really a no-brainer. If you can, you should do it, especially C++ 17 that has guaranteed copy elision for the kind of case I just described. And of course, if you look at the top right, there's this like a little rules table, how you're supposed to pass parameters in and take parameters out of C++ functions. Whether it's a lot of data, a little bit of data, is it worth the copy? Should you use a reference, a const reference? All these little things help the compiler build you faster assembly code. This is taken from, I believe it's the C++ core guidelines. So if you have the time to take a look at performance section of the C++ core guidelines, this is a document online on GitHub that the creators of C++, the ISO CPP committee, many members contribute, and it contains a wealth of advice for all sorts of different situations on how you can use C++. It's a wonderful resource with examples. Yeah, if you don't have some kind of coding guidelines in your company or in your group at the university, it's a very useful thing to adopt. All right, let's get into data structures a little bit. So we all use them, we all need them. From what I've seen in the last whatever amount of years that I've been doing software development and the way that I was taught back at university, typically I was taught object-oriented programming, as with many people, as the be-all end-all of programming, which does not necessarily have to be the case, right? If you're doing MATLAB development, you're probably not doing object-oriented programming. Python as well is also very procedural, functional language. It can be used this way. So I would suggest, aside from when thinking about making a data structure to use, aside from thinking about what does this data structure need to contain, what data does it need to keep, you should also take into consideration how it's going to be used. And that part can really bring a lot of speed up. And I will show you exactly how much on my machine that is. Preferably, you want to keep your data structures short so that they fit in a cache line if possible. One cache line is 64 bytes. And as I mentioned, if you do a fetch from memory, your program needs some data. It's not just going to get a number or two, it's going to get 64 bytes, a whole cache line. And if your entire object exists in that single cache line, it's beneficial for you. Or if an integer number of your objects exist in a single cache line so that one object is not split up in two, it's beneficial for you. But let's see a little bit that in a bit more detail. So let's imagine a situation that I'm writing a piece of software that is dealing with images. It's dealing with pixels, and the algorithm that I'm writing for, I'm going to write the structure specifically only for that algorithm. Let's say the algorithm that I'm writing for needs to know a few things about the pixel. It needs to know the red, green, blue and, channel and the alpha channel of the pixel. It needs to remember which row and which column this pixel came from. So we're looking at the top structure now, struct image AOS. uint32 row column. It needs to know some distance to something, I don't care, and it needs to know phase, whatever, right? And I know the data types of the data that belongs to each pixel, and I create a structure like this because that's the first thing I would do. That's how I've been trained to do, object-oriented, each pixel, its properties, boom, there's a structure. And since I know, let's say that my image is 5 million pixels, I'm going to create a vector of those pixels so that I can work with it. Excuse me. And then now I've shortened the code here, but then I'm going to also make some kind of interface of this class so that other classes, other parts of the code can use this class as well, the image AOS class. And let's say I want to do an operation on all green channels of all pixels, of any pixel, and I create a function here, uint8 get reference get r green channel with an index, and it returns me the green channel, so that would be a byte out of some pixel at index idx. Or we could do it a slightly different way. So in the bottom, struct image SOA, it stands for image structure of arrays, I could define 1, 2, 3, 4, 5 vectors where only green channel, sorry, more than 5. That's it. One vector for each of the channels, one vector for rows, one vector for columns, distance, and phase. So now I've simply restructured my data because I know how I'm going to use it in the future. And now I have one structure of 5, 6, 7, 8, 9 vectors instead of having one vector full of structures that have, 9 fields. However, I define the same interface, get our green channel. It will return the same value. The only difference is that the underlying representation in the container is slightly different. Right? The bottom one is ordered, green, 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 red, 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 and the top one is ordered, red row distance phase, or red green BA row column distance phase, and then the next pixel, that information. I'll visualize it in a second. The point I'm trying to make is it's your choice how to organize the data in your structure, and it makes a big difference on how you do it depending on how you use it. Some of you probably already know a difference between the structure of arrays and arrays of structures. And yeah, two classes can do the same. They can have the same interface. Let's make a little test, right? So test is to update the green channel of all pixels. And we use 10 million pixels to do this. And we use O2 here, so the optimization level 2. This is /O2. I'm using Microsoft compiler to do this. So for arrays of structures, this is how I would write it. So for I to 0 to number of pixels, I want a pixel at index I, its green.g, its green channel, and increase it by 1. With structures of arrays, I would sample all greens at a certain index. That's going to be the green of my pixel that I want, and increment that by 1. And the last example here, I'm not going to go into detail about because that comes in later in the talk. And this is the vectorized version of the same thing. This is just a little taste of what it can achieve. So if you write a single program like this, and I just run it and time it to as precise as I can, you can see the difference in results. So using arrays of structures, update AOS took 187 milliseconds. Structure of arrays, not vectorized, so the basic one, the middle case here, 38. So what is that's a factor of 5, 6. It's quite a bit. So we've achieved a 5 times speed up. 3, 4 times speed up simply by reorganizing the data in our container and doing pretty much nothing else. And if we decide to vectorize, in fact, the machine did all the vectorization for me, we can reduce that down to 5 milliseconds. So updating the green channel of all pixels in your image can take anywhere from almost 200 milliseconds to only 5 or 6 milliseconds, and we've changed almost nothing. So this is to show how small changes to your data structures can bring about enormous speed ups. And why this happens is the topic of the next slide. And I can tell you in one word already, it's because of caching. So let's take a look at where caching helps here. If you remember earlier, I told you that when you're grabbing a number from RAM, in this case the green channel, you're actually not grabbing only the green channel. You're fetching, which is the technical term. You're fetching 64 bytes around it, and we have an idea of how large our object is. Well, maybe a question for you guys, if we can stop for a second. If I were to do size of image AOS, what would I get? And I'll give you guys a minute. If anybody knows, you can write it. Nobody knows. I tried to do a little calculation here. What would size of be? What's the size of the structure? So RGB and A here are 8 bits each. Because of padding, 68. Not quite. Not quite, but better than 28, yes. So RGB and A are all 1 byte, so that's 4 bytes. Again, the top structure. Correct, Mislav. Yeah, 32. So row and column are each 4, so that brings us to 12. Distance is 8 and phase is 8, so 28. However, padding, right? As Mislav already figured out, padding is important, and I'll show you why. So it's not intuitive. You would think it's 28, but it's actually not. You can force it, but that's a different topic. So if we take our standard structure of arrays approach and we look at how much of this object fits in a single cache line of 64 bytes, assuming it's aligned to the first byte, and this is typical. So let's say it's aligned. We're looking at the start of our array of structures. We can pretty much see this is RGBA, 1 byte each, then row and column, 4 bytes each, and then distance and phase, 8 bytes each. If you naively add that up, it's 28 bytes. Okay, that's the first pixel. And the second pixel would be from byte 28 to byte 56 or 55. That would be the second pixel. And then the third object would be byte 56 to something, but you know that it's going to be split between the two cache lines. So if you're grabbing the third object, so the third structure in this array, you're going to have to do 2 fetches, one for the first cache line and then one for the second cache line. Maybe you hope that the first cache line is still in cache. In some L1, L2, or L3, it probably will be, but you still have to do 2 fetches. One will be probably faster, but there's no actual guarantee that it will be in cache. So and then this pattern will repeat. So only I don't know, every 4 or 5 structures you will actually get the start of a structure aligned to the cache line. This is not efficient. So for pixel I is 1 load instruction. I plus 1 is also one a load instruction, the same one. But the third one, you have to do 2 instructions, and that's not efficient. So your load efficiency rate is less than 2 out of 64. However, if the compiler does some padding for you, and here it did, in fact, it added junk after the 28th byte. Up to 32, it adds junk, so that if you pack 2 of these objects together, they will equal 64. And then you always know that for one fetch, and remember, the fetch is where the time goes, always. The computation is essentially free. It's getting the data to the CPU that's the problem. And here you ensure that for every fetch, you will always get the 2 numbers for any I, any index. Sorry, 2 structures. And you get a load efficiency of 2 over 64. Let's see what it looks like if we use arrays of structures. Sorry, structure of arrays. Since our problem says we want to change only the green channel of all of our pixels, and I use structure of arrays, I have an array with only the green channels. See here in the previous example, we would fetch very efficiently 2 structures out of memory, but we would change only 1 byte out of the 64 bytes, actually 2 bytes out of the 64 bytes. So in terms of a computation per byte, it's very, very, very inefficient. We load 64, we change 2 bytes, the green channel of 1 and the green channel of 2, and then of the second one, and then we move on. We throw away all the data that we had painstakingly obtained from RAM. That's pretty bad. So if we reorganize data such that only you get only green channels in a single array, for one fetch of 64 bytes, you get to use all 64 bytes. So all green channels here will be changed, will be switched based on only one fetch. So you get 64 operations for one fetch, which is great success. So and loading efficiency is 100%. So, however, yes, our test case is perhaps somewhat idealized. We want to change. Maybe your program doesn't require you only to change a channel or only to change the row of all pixels, and it requires more random access than that. And then you start investigating, and you perhaps find some useful middle ground. Say we often need to change. Sorry, Kobe Browning's a question about the performance test. Is the compiler never able to vectorize the second for loop? I'll have to look into that a bit later. Whether the compiler is able, never. If it's using structure of arrays, I would say never. It could decide that it will do it through some kind of masking if it knows that only the first, second, third, and fourth object in your field in your array is repeatedly used. It may try to vectorize, but it will be very inefficient due to masking. This is down to the compiler's intrinsics. It makes a lot of decisions on its own. I would not count on it, but I would check. So that's all I can say for now. So in this idealized scenario, we are only changing one channel at a time. But what if we know that we're going to be working with RGB and very, very, very often, and we would like the 4 of these channels to be together always? And we can just make an intermediate structure that serves, again, the two needs of the data structure: what it needs to know, and how is it going to be used. You can make an intermediate solution that looks like this. So struct RGBA, you still have a small vector of structures, which is the first vector here, and then the rest is the same. Yeah, so it's really up to you to try to figure out which fields in my structs are accessed frequently. They should be close together, packed, yeah, and which are not. And that depends on what it needs to know and how it's going to be used. So you have to know something about how it's going to be used a priori. Summing it all up together, yes, arrays of structures on the left side, all-purpose and slow, probably slow, unless you really always frequently in your algorithm use all of the fields, which is unlikely. The other side of the spectrum, which is a very specialized structure of arrays, over-specialized and fast, and something at the end, at the right side, a specialized realistic scenario, I would say. One more tidbit. So arrays of structures are associated normally with object-oriented programming. And that's how I was taught. And normally I would, in non-optimal code, I would just think through what the data needs, what this structure needs to know, you know, a person, name, last name, phone number, address, whatever. Just throw it in without a second thought. But if it's part of an algorithm that needs to run fast, you should probably chop these up into substructures and test to see which one yields best performance. Structure of arrays is associated with data-oriented design. So it's a different programming paradigm, which all of you, many of you, I'm sure, are familiar with as well. Like if you're using MATLAB, you're probably doing data-oriented design already. Next point, it's hard or impossible to vectorize non-contiguous operands in arrays of structures. So in terms of vectorization, and I've not introduced it yet, vectorization means that, well, there are certain units on the CPU that are able to perform an operation, like an addition, for example, on more numbers than just 2. It can operate on arrays, let's say 4 numbers, and you need to multiply these 4 numbers with the next 4 numbers, and it's going to store the pairwise multiple or sum in a different array. So for one instruction, you can get 4 results. In so-called Flint's taxonomy, that would be called a single instruction, multiple data. That's vectorization. Right now, we're not dealing with it, but it can, and it should bring about an enormous amount of speed up, as you've seen actually in a few previous slides. 5 milliseconds to do the 10 million update. And vectorization you can do manually, but it's typically done by the compiler for you, is very, very sensitive about the data layout. So it can only do proper vectorization, full vectorization, if the data is compact. So say you want to add up green and red channels, it's perfectly vectorizable because all the green channels and all the red channels have their first 4 values right next to each other. But if you use arrays of structures, you know that your first red channel is 28 bytes away from the next. No vectorization, okay? Results may change somewhat if all members are used, of course. And padding helps performance. It's automatic, but it can be counterproductive. For example, if I were to transfer this structure over the network and I have to serialize the data, right? Serializing the data that is padded is not a good idea because you would be adding the padding, serializing the padding and unpacking on the other end with unnecessary junk in there, right? But you can't do it with Pragma Pack 1. And I think this is, yeah, this should be true for all compilers. Okay, Am I going a little too fast? Is this understandable to most people? Okay, thank you. Okay, so to conclude thank you. To conclude the story about data structures and performance, maybe just a little bit of quick overview. Data structures should be informed by number one, and again I'm repeating it, what they need to know and how they will be used. If you're interested in performance, it's always good to look up what is object-oriented versus data-oriented design. And to that end, and I will all the links are at the end of the talk, but to that end, I would really strongly suggest looking at the CPPCon 2014 presentation by Mike Acton. He is, I think, the general software manager for Sony or some highly acclaimed gaming studio. I don't remember the name, but they use data-oriented design for the generation of their games and have very strict, almost dogmatic, but not quite, rules about building software. And his talk is the highest rated talk of all CPPCon talks. Mike Acton. I'll leave a link later, but it's a very interesting and an opinionated talk about performance in C++, and I highly encourage everyone to take a look if you're interested in data-oriented design. The next piece of advice is use cache-friendly structures. So cache-friendly here simply translates into is the data that I need right next to the data that I will need very soon. And that's all it is. So if you're using, for example, a standard map, std map, you know, your keys are here, but the values can be anywhere in memory. They can be anywhere, and the keys will contain a pointer to the data. So currently in C++ 2023 or any other previous version, for an unordered map or for a normal map or ordered map, there is nothing in the standard forcing the storage of values to be contiguous in memory. So not a good idea to use a map if you're interested in performance. Or you can wait until C++ 26, hopefully, adopts the flat maps or flat sets that will have this guarantee. Again, it depends on your use case. Maybe your use case is I just want to have a map that you know binds a key to a value. I don't use it in my hot loop. I don't care. But if you're using it in a hot loop and you know that you have to iterate over values 1,000 times a second, then you really want all the values to be contiguous in memory. But this is functionality that C++, the standard library at least, does not have at this point. You can find this functionality in, for example, EA, so Electronic Arts, the game publisher and developer. They have a EA STL, so they implemented STL for themselves, and they have these cache-friendly maps as well. Vectors, by definition, they are contiguous. Vectors of pointers don't need to be. Yeah, so pointer chasing is a thing where we're going to get to that as well, etc. So just know your structures. Variables you access often together should be close to one another in memory, and we've seen that with an example here. If we know we're going to be using RGBA often together, put it in a struct, run the system again, keep the interface the same, so it's like a localized change you can test. Have a timer class in your code. You can run before and after. Boom, you get your answer rather quickly. Use array of values instead of array of pointers. Yeah, so pointer chasing is not something we're dealing with yet. It comes a little bit later, but yes, the fact that pointers to objects are contiguous, let's say in a vector, means nothing for performance. In fact, it means it's a detriment to performance. Okay. So let's briefly look at that specific topic. Yeah? So what do we, how do we handle iterating over a large number of values if they are not contiguous, and should we do that? The name of the topic is reference types, value types, and performance. If you're using a lot of new and malloc, or if you're manually creating pointers, you're using reference types. And if you're working with actual data, actual objects in their own locations, not pointers to them, then you're working with value types. So let's see what kind of performance impact we can get. We accept as the price of dynamic polymorphism. So when I was studying object-oriented programming, we always said there's 3 features. I don't think there's an actual agreed upon definition about what object-oriented means, but we mentioned 3 features of language that are required for a language to be object-oriented, and that's encapsulation, inheritance, and polymorphism. And in C++, I certainly see a ton of code that has rather deep structures in terms of inheritance. If you're using these kind of deeper structures, are using inheritance in performance-oriented code, there might be a penalty that you are paying that might not be necessary. Again, this kind of this topic has a lower impact than using the right data structures. You could be using the right data structures in getting a tenfold speed up, whereas just switching away from dynamic polymorphism to maybe static polymorphism using templates, but we're not going to go that deep, or using unions, it can bring about a good performance benefit. And let's see how much that would be. So what I'm going to show you is a textbook example of some shapes, circles, triangles, rectangles, and we're going to try to compute area, an area of these objects for many objects, and see how long that takes. And then we're going to try to implement the same thing using static polymorphism, using modern C++ features like std variant, and see how long that takes and why that might be the case. As to why that might be the case, I only have a certain amount of understanding. This is a deep topic that I don't have a fully comfortable understanding of, but I know enough to be able to know what I can use or cannot use in my code. Another point that I didn't make so far is that this kind of presentation, I don't like generally looking at these kind of presentation online for one reason, and that's because it simplifies things. Most people, I assume most people that are here, they don't have full control over the code bases that they are working with. So when I say, well, just change your data structure, this or that, you might not have the ability. You might not have the ability to upgrade, update your C++ compiler. I just want to say I understand. Some things you can, or some things you cannot do. It's just not up to you. But for example, in the example that I gave with the data structures, the interface of the class really can remain the same. So you can kind of surgically go in there and maybe change something for the better dramatically. But aside from that, I understand you can't just come into a large code base and start saying, I'm not going to use polymorphism at all. Anyway. So let's take a look at the top left of the first image here. It's a shape base. So it's a base class for any shape, and the default constructor empty, and then actually user specified constructor empty, and a pure virtual function area. So when other classes inherit from shape base, this will force them to implement area, implement the virtual function. And we have 4 classes that do this. So square, rectangle, triangle, and circle. They all have different ways of computing their areas. And the magic of polymorphism in C++ is the following. So you can have a pointer to a shape base, and if you ask this shape base to give you an area, the base shape will know which actual type, which child class it is, and invoke the correct area from the correct child. So that's the magic. But there's really not that much magic in there, is because what happens is that the child has to keep track of its own identity, and when you invoke something through its shape base, the shape base will also know, because it has written the class structure, the class layout has changed. There's a virtual function pointer in there that determines the identity of this child. So it's all written down, but you have to be aware that that additional pointer, the virtual function pointer table, is also part of your class. It's not just RGBA, row column phase anymore. There's another one. It's hidden, but you should know that it might mess with your cache lines. Anyway, and so what we can do with this is we can make a vector of, I don't know, 20 million shapes, base shapes. We can fill that vector at random. Well, let's say the index at 1 is going to be a circle, at 2 is going to be a triangle, at 3 is going to be a square, etc., etc. And we just call the base shape and ask the base shape for area. The right area will be computed. And now the trick is, what happens if we just take a single shape and compute the area of all circles, or if we take only circles and triangles and try to compute the areas of all of those, or if we take at random 20 million shapes, some are square, rectangle, triangle, without any regularity at all. Interestingly, the results will change dramatically based on what actual shapes we are computing, and not because their area calculation takes more or less time. No, it's simply because of reasons I'll get to in a minute. But let's try to implement this in a statically, let's say, statically polymorphic way. Maybe first a quick question for you. How many of you know? Do you guys know what unions in C are? C or C++? Unions. Okay, 1, 2, 3. 3 out of 55. All right, let's take that as a represent 4. Yeah, that's what I thought. Yeah, there's not much magic. Thanks, guys. There's not much magic to it. So for the others, a union, by using a union in C or C++, what you do, you say, I want to have 16 bytes, and I want to put in there whatever I want. I'll keep track what's in there, but my data size is 16 bytes. I can use it for whatever I want. I want to put width and height in there, fine. I want to put radius and nothing in there, fine. I want to put side in there, fine. It will always take 16 bytes, but you have to keep track which object, which type is actually in there. The C programming language is not type safe, so you can easily kind of shoot yourself in the foot here if you are grabbing the wrong type, if you didn't keep track. Correct. Yes, Oscar. So like a container for a set amount of data. Yes. In C, you have to keep track of what data you put in there. But in C++, you don't if you're using, for example, variants. I think std variant is also C++ 17. Yeah, std variant is std optional in these kind of malleable state objects. So, excuse me. So in using std variant, we can say, I want a vector of 20 million objects, and they're all the same type. They are std variant. And this variant can be either can contain either a square or rectangle or triangle or a circle. And the second line of code on the right side defines that. So a vector of variant that can contain 1, 2, 3, 4 options. The line above that, the template, this is a convenience function. You can just find it on cppreference.com, but don't look at it. It's tricky. Anyway, what you can do then with this variant is for each of these variants, they will know their internal state. So the variant will remember, unlike the union of C, will remember which type am I holding from all the types you told me can be in there. Yeah. Yes, Daniel. Yeah, a set of types. Provided that the largest type is covered and all the smaller types are covered automatically. Yeah. So the std variant will actually remember its identity because you told them which types can exist. So when you create a variant, it's going to know, boom, I have a square in me currently. And if you try to grab a circle out of me, I'm going to throw an exception. Yeah. For example, I'm going to throw an exception. So now you can store all the data in 20 million in a 20 million long vector of only variants. boom, 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 and they will all take the same amount of bytes. It's 16 bytes, and you can just iterate through them and invoke the function that you want, and you can just do it using lambdas, again, a bit more modern C++. And if the lambda detects, and it will do this statically, if it detects I have a circle, it's going to return automatically a function. Actually, it invokes the lambda that returns the area of a circle. If it detects it's a triangle, it'll return. So this is polymorphism, but in a slightly different way. And most importantly, it involves no pointers. So you're working here with data types, value types, and not reference types. So you don't need to, for every index of your vector, go somewhere else, check which type this object is, check its virtual function pointer table, find the function you need to run, circle colon colon area, and then execute the code. So there's two levels of indirection that you avoid by using value types. Of course, there are benefits and detriments to both cases, but you should be aware that this is an option, especially for small data types or for sets of data types that are not too dissimilar, that are not too dissimilar. And in my case, I have 4 data types: square, rectangle, triangle, and circle, and they are relatively similar in terms of their size, the data size. 16 bytes is maximum. If I had a circle, a magical circle that requires 15 data fields, it might not be the best idea to do this. So allocating 50 million shapes and computing the sum of their areas. We repeat this 20 times, so that's our test, and we get an average. I think CRTP is the way that variants are implemented, Nicola, but I'm not sure. Again, I don't know much about how they are implemented, but if you look into it, it's probably CRTP. Polymorphic types access through their pointers. Yes, they can be anywhere. And variant types rely on compact structures. So of course, some space is wasted. And let's take a look at the results. So the first 3 results are results from invoking the virtual function. So from standard, I would say more common sense, more usual polymorphism provided by inheritance in C++. And the last 2, sorry, I'm a little distracted. Yeah, so curiously, recurring template pattern is how variants are implemented. So I don't think there would be, I'm talking to Nicolas, I don't think there would be any performance difference at all, but it would be a wonderful test to try. Anyway, that's a cool topic aside, but yeah, let's get back into it then. So the first 3 results are all standard dynamic parallelism, dynamic inheritance, and the last 2 are the results using variants. And what we see is something interesting. So how we organize the data, if we are using normal polymorphism, how we list those objects makes a difference in terms of how performant it can get. But let's take a higher level view. So first, simply using variants yields an 8.3 times performance increase. Why? Because for variants, you don't need to evaluate 2 pointers and go to that location and find another pointer and then go to another location. Oh, I have this is my function I need to execute and then execute it. It's unnecessary to do all that jumping. That's called pointer chasing. And another issue is that the memory is not scattered. So by definition in C++, if you're using dynamic polymorphism, standard C++ polymorphism, you are accessing the children of a certain base class through their pointer or through their reference. And that's the issue. So that pretty much guarantees that they're not going to be contiguous in memory. You're going to do new allocation and they can end up anywhere. There are ways of forcing your those objects using placement new or something to be contiguous and then having pointers to something you already know the location of. It's weird. But typically that I've not seen that happen. So if you just use the basic dynamic polymorphism, you get versus variance. If you can use variance or unions, you get this amount of speed up in my example. Now, predictable versus unpredictable access. If you just randomly issue these shapes versus having some pattern like ABCD means triangle, circle, something something, triangle, circle, something something. The CPU is going to figure out. So the prefetcher has figured out that you have a pattern in here, and while it's executing one, it's going to start prefetching the next one because it kind of figured you out. And that's already a huge speed up, 2.5% essentially for free or for making your objects predictable. This variant doesn't care about order. From the CPU's perspective, it's loading the same type all the time. This is a slightly more involved case. You would expect if you repeat the same shape dot area, so shape colon area, and if you repeat that many times, that means that the instruction cache for that specific function should be very fresh, should be hot in cache, and it will never have to be swapped out by the next object. Even if it's predictable which next object comes in, those cache instructions can get evicted out. But if you repeat the same call, say circle area, many times, it keeps the data fresh, and the CPU never has to go and find the instruction for triangle that area. But I didn't get a large speed up in my case because I simply think that there's not enough instructions. Computation of area is only like 5 or 6 instructions, so it's all in L1 anyway, all four, and L1 instruction cache anyway. But that's a theory. I haven't tested that. Okay, so now we have to move on to vectorization and parallelization. This is sort of more, I think, a little bit easier to follow part of the talk, but I suggest we take a little break, maybe a 10-minute break, if that's okay with you guys, just to freshen up, grab some water. We've already been going at it for a while. Okay. I will leave the camera on. I don't want to stop anything just to avoid any kind of, but I'll be back in a few minutes.
Okay.
Thanks, guys.
I'll
Take
put
care.
the slide on just to announce the break. How much time do you like for a break?
I would like 10. I think we can live with 15 minutes as well, actually.
Okay.
If that's okay.
I'll just put that on a whiteboard.
Perfect. Thank you, guys. See you in. Thanks, Hertel. See you in 15 minutes. Yeah, if you have any questions, you think of them, anyone, you could just put them in the in the chat. I'll get to them in a minute. Okay. I hope you guys are back, feeling all refreshed, ready for another, well, for another hour of this. I think this part of the talk will be also quite interesting. I hope so, at least. This next section is about vectorization and parallelization. And then after that, we're going to talk about the compiler and how it can help us or how it can do the opposite and how we know what it's doing, and maybe try to see things from the compiler's perspective. And after that, we're going to see a use case of an algorithm that has an implementation already in OpenCV and how we can make that faster using some of the principles we've seen in so far in the presentation. So yeah, let's start with vectorization and parallelization. So for those of you that are not aware, every modern CPU, at least every X, x86, x64, x86 CPU has vector units. I'm pretty sure ARM has as well, but I have not worked with it myself. But it's a special set of units. It's dedicated hardware on the CPU designed to operate on multiple values in a single clock cycle. So I've already mentioned that, right? So if you have two numbers you want to add, you can do that using, according to the taxonomy, a single instruction, single data. That would mean two operands, one result, or one operand, one result. Or you can do it using these special units called vector units on the CPU. That would be single instruction, multiple data. There are other other classifications, other parts of that classification, like single unit, multiple thread, which you would then apply to GPUs, or multiple instruction, multiple data as well, which I don't know if it exists in practice. But okay, so we are here working with vector instructions. Typically, if you hear things like SAC or AVX instructions, these are the instructions that I'm talking about. And you could have, or the latest technology called AVX 512. So I think the latest generation and the previous 13 and 12 of Intel's processors, I think 12 also has AVX 512, and AMD processors have now support for AVX 512 as well with the Ryzen 7000 series. What that means is right now you can, if you have a vector of operands, let's say A's, a vector of B's, and they're all nicely packed, you can produce a vector of C's, which is a sum, a multiplication, a logical operation, whatever. There's many of these instructions, and you can operate on 8 numbers at the same time, or 16 single precision numbers at the same time, which is a huge increase. So these next few slides are about what kind of performance gain can we get. Typically, it's not times 8 or times 16. It's slightly lower, because it's not just about how fast you can process. You have to feed the data. It's also about how we can see whether this is actually happening. You want this to happen, and how we can help the compiler do it. And one of the ways we can help the compiler vectorize the code for us, we've already seen in the first part of the talk, and which is to pack your data up properly, so that you can actually, fetch 16 doubles and put them in these registers, fetch 16 doubles for the B operand, put them, and then run one instruction, you get 16 results. It's a amazing thing, and it should be exploited to the maximum extent. Maybe worth mentioning, it's a little bit more expensive in terms of power. The CPU cannot run at full, I don't know, 5, 6 gigahertz maximum overclocked. It won't do that with AVX instructions. It'll downclock slightly, but you still win, and you win big. Can lead to significant improvements, but also small drawbacks. It's more difficult to work with. It can be quirky, and you might need to nudge the compiler in the right direction. Also, tooling becomes important. So I've seen in Microsoft Visual Studio, I don't know which tools you use, it's a constantly evolving topic. So the compiler needs to be able to tell you why has it or has it not vectorized, and why, and what you can do with what you can do to make it happen. Basic implementation is low-hanging fruit because it's already done for you. So typically, it's already done for you if you're using O2 or O3. In your release builds, you're probably using O2 or O3 optimization compiler flag. And which instructions can you actually use? So you should be able to know which CPU you are running on. Again, important to know which architecture you're supporting. Otherwise, which is one of the reasons why I always compile, if I can, I compile the code that I download online instead of just taking in a compiled executable. If possible, it's probably a better idea to compile it. For example, if you take a look at the GPU server that we are using in the company, I know that it supports, you can see the red arrows here, bottom left, SSE, SSE2, and AVX2 instructions, but not AVX512. This is a, well, now last generation AMD EPYC Rome 32 core processor, but it does not support AVX512. So if I were to compile with full optimizations that uses AVX512 instructions, it would not run. So you should inform yourself about what hardware, if you can, what hardware am I using, and should I recompile or not. On Windows, you can check which instructions your CPU supports by using CPU-Z. That's the default go-to software. And if you just Google any of these, AVX2 or FMA3 or SSE 4.2, you can find a list of instructions and all their explanations. And like adds two numbers 8 wide, adds or multiplies two numbers 4 wide, or does a logical AND operation 8 wide, etc. So the quick question is, I already have the important question is I already have some code and I want to know whether it's actually being vectorized or not. And the answer to that is normally it is being vectorized because the compiler tries to do that as much as possible. Yeah, so it's smart enough to see, well, look at this loop, I can probably vectorize this. If you have a very basic loop that just goes from 0 to 10,000 and all it does is increments a certain value and all the data is in a vector and it can do the reasoning. It can know that, for example, the induction variable, the I typically, jumps only one spot and not 3, so I++, instead of I plus equals 3, or that the end determination condition is a constant, then it knows that if it's working 8 wide, it knows exactly how many times it has to execute the 8 wide operation and can mask out the last few executions, right? It can even unroll the loop and hard code all of that in assembly. So it's important for it to know certain things so that it can do the auto vectorization for you. Otherwise, you can do it yourself using intrinsics, which are again available in all the compilers. And it's a little bit more work. And then if you do that, then you're locked in, right? So if you recompile for another machine that doesn't have these intrinsics, it's not going to compile. So the compiler can give you hints. You can ask it, like, here's my code. I want to know what of this have you managed to vectorize and what did you not manage to vectorize. And if you do that in a normal test application that I've used, so this is a small application, you will get something like this, the output. So for example, much of this is from the standard library or Microsoft's internals that were not vectorized due to whatever reason. And unfortunately, and this is why I say tooling is important, I have to go online and see what these codes mean and have a certain explanation of them and examples of how yes, it works, how it doesn't work, etc., etc. So you cannot expect the machine, the compiler to vectorize absolutely everything, but your code at least should be vectorizable if it's possible in theory. If you can restructure your structures so that the stuff that you are vectorizing over is contiguous, that would be great. So again, many rules on why it doesn't happen automatically. If you run the QVec, so QVec report 2, for example, I think that means report everything that has been and that has not been successfully vectorized. This is your output, and then you have to go one by one and check. And here I also force it to vectorize using only AVX2 instructions and not SSE. And these are some reasons why it may not happen automatically. So if the loop contains some control flow, so you have your induction variable I and you're not adding all of your, so you have, let's imagine you have two vectors, each 10,000 numbers long, and you're not just adding them up and putting them in a vector, which is a more common thing to do. You're not just typically not just adding things in a loop. If you have complex control flow in there, say every third, every fourth, this is something that the compiler might still understand, and then mask out, index 0, 1, and 2, and the third it keeps, 4, 5, or whatever, and the rest it keeps. It might still decide to do the vectorization. If enough work is being done, it's not going to recompile twice and optimize this number. It's going to make a mask for you and ignore the rest if it's worth it. But that deduction, that kind of reasoning is left to the compiler. You should have, if you're interested in performance, a way to have some kind of dialogue with the compiler. Why I didn't do that? Try to restructure, run again. If you have an if statement such that, let's say, every odd index is added and every even is not, you might want to separate that into two, or let's say the first half of that big array is addition and the second half is multiplication. You can make that into two. You can split that up into two arrays or two for loops and see if that gets vectorized automatically. So there are a few things you can play with, but I can't go into detail this much because I don't have enough experience, and because the rules can be complex and unintuitive as well. So for example, do while loops don't work with Microsoft Visual Studio C, C++. For loops do. Go figure. So this kind of stuff is a matter of research as well for them. But one thing, okay, maybe explain it better here. One thing that it definitely needs to know whenever it's vectorizing, the compiler needs to know that the induction variable is stable, so that it does not change within the loop itself. So if you're looping from I equals 1 or 0 to I equals 10,000, nothing inside the loop should change I in any way, because if it does, it's not predictable. Even worse, if that change happens in some kind of if statement, it's not going to do this reasoning for you. You have to make sure that it's a very simple loop before it starts executing. Now let's check. So we have all this output from the compiler. Let's check what it actually did, and maybe we get an idea of why it did what it did by looking at the assembly. So in Visual Studio, it's very easy to look into an assembly of a snippet of code. It's even easier if you use things like Godbolt or Compiler Explorer online. You can just paste a snippet, choose your compiler, and it'll give you the assembly. I find it convenient also just to use Visual Studio here. It's convenient also because you can step through the assembly code as well, just like you would step through the higher level code on the left. So as you can see on the left side of the screen, I created a breakpoint, and my caret, so my indicator, is top left, the yellow arrow, and that's where I've stopped my program in the function called for loop. And here all I do is just iterate from I equals 0 to the end of the vector, vec, which I pass in by reference, and I just increment it by 1. And interestingly enough, this loop was not vectorized. Now, why do you think that is? For example, I know that vec.size is not going to change the size of the vector. So induction variable I has to be stable, and the size over which it's iterating has to be stable. What we do with the vector inside is very predictable, very easy. I just increment it by 1, but still it's not vectorized. And later on, if you read the messages from the compiler, it says that vec.size cannot be proven not to change the size from within. And that can be very easily solved by the next function, for loop vectorized. If you see from lines 18 to 24, it's essentially the same thing, but we make the terminator, the end index of the for loop, into a local variable. And that local variable is very easy to reason about because my function is very simple here. It knows that mux does not change, and therefore the compiler decides to vectorize the loop inside for loop vectorized function. And that's all it took to speed up the code by a factor of 6 or 7 in my case. But I was going to talk about a little bit about the assembly that's generated. So if I were to step through the function, so my caret, my indicator is on the top left, the yellow arrow, but I'm stepping through the assembly code. If I were to step through repeatedly, my indicator, so the caret would go in circles in the area of the red rectangle. So I know what it's doing, and I can take a look at the instructions. So wondering whether something was vectorized or not, okay, fine, you can do that. You can even ask an optimization report to tell you, but the bottom line in the end is what is the assembly code that's generated, and you can take a look at that easily. So you see the instructions, you can just Google them and see, are they AVX, are they SSE, or are they not? In fact, here the optimization report told me that it's not using any kind of vectorization, but I can see that it is. It is using something. It's using VADDSS. It's using XMM1, XMM6. Those are registers that should be used for vectorization. So these are wider registers. They're not just one double or one float. They are 4 wide, in fact. And if you create a watch in Visual Studio to see what they contain, at the very bottom left of my screen, you will see that XMM1 contains 4111 and XMM6 contains 1111. So if I were to iterate now, which I can't because this is a picture, if I were to iterate, what I would see is 5111, 6111, 7111, etc. So that tells me that the machine is using an SSE register used normally in vectorization, but it's not vectorizing. It's just using that register, the first 4 bytes of it, and nothing else. And the bottom register contains the increment that we are using. So it pays to know a little bit about the assembly code that's generated, because in the end, that's the bottom line, no matter what the optimization report on vectorization tells you. Now we're going to take a look at the second function, so line 18 to 24, which is the vectorized version of the loop, and I'm going to take a look at the assembly that is generated. And now here I'm absolutely sure that it's vectorized, because I can also, again, read which functions are being, which assembly instructions are being used. I know they are AVX this time, and I know that the registers used to store the data when it comes from RAM ends up in registers, but here it ended up in registers belonging to the vector units. And I can also be absolutely sure that this is happening because I can check again the content of those registers. And these registers, YMM1 and 2, again, bottom left of my screen, they are 8 wide this time. So 8 wide, 4 bytes, F32. Right? And if you see their contents, 101, 102, 103, 104, and the increment again below, I know that it's actually doing the work 8 wide, which is my goal. So this is a very short story about vectorization. There is so much more to talk about. You know, what is the realistic thing you can expect from the machine or from the compiler to give you? How can you help it? What are the tricky bits? But how to write the intrinsics yourself? What do you do when your data is not a multiple of 8 or 16? So how do you do the masking? Shuffling operations. There's so much more to do, but this is not, again, the talk is more higher level. What can you expect? How can you get a little bit into it? Now, the same story with parallelization. Only one slide here. So if you're not aware, the at least Microsoft compiler will try to auto-parallelize your code out on its own. And so it might run Ilya Artyushin will non-vectorize snippet, which is XML throwing a CPU frequency. Good question. I don't know. I just don't know. I've never tested that. It's possible, but I just don't know. I don't know. So for parallelization, starting with C++ 17, many of the algorithms in the STD algorithms library, so standard library, a huge collection, containers and algorithms, starting with C++ 17, many of the algorithms in the algorithms library received parallel implementations. And you can do many of these, you can perform many of these algorithms in parallel simply by adding one additional argument, which is the executor, before, say, sort, or before accumulate, std sort, std accumulate. This, to me, is a huge benefit. So if you're using modern C++ and you want to see what your code will run in the how your code will run in a multi-threaded fashion, you don't have to anymore. You don't have to start coding, type 4 new classes, make a runnable class, implement this interface or that interface. It's lines of code just so that you can check whether your code would benefit from it. No, you just use std execution namespace and put it in front of sort, transform, for each, reduce, whatever, depending on what your algorithm is doing. And even if you don't do that, loops can be auto-parallelized as well. And you can also try to nudge the compiler into auto-parallelizing your loops, something very similar to OpenMP, where, say, you have, again, 10,000 elements, and this time you do much more work per element, right? So you're not just incrementing a value of, a vectorizable thing, but you're doing complex work in there, maybe 200 lines of code. You can tell them, the compiler, can you please try to parallelize this for me, and just chunk it up. You get 8 threads to play with, and actually I'm pretty sure you can't say how many threads you can use, but can you please chunk this up for me? And then it will, in the most basic sense, you have control over this, but in the most basic sense, you can say, divide it into 8 chunks. I want first thread running, this thread running, etc. Provided the data is completely independent, which is the tricky bit, right? Because it's not going to do mutex locking and unlocking. It's not going to guard your data at all. Something to be aware of, something to look into if you have simple code that does a lot of work and does not require atomics or mutexes, condition variables, etc. And not all functions in the algorithm are parallelized, but many useful ones are. For example, sorting. You have large objects you want to sort, and there's 50 million of them, and there's no better way, no easier way than to just say sort std execution parallel here in the second sub bullet, or parallel unsequenced if you know something about how the data behaves, and just see what it runs. And I'm going to actually do that in this example in a second. So low-hanging fruit, but has similar quirks to vectorization, and you do have to talk to the compiler. You need to know, you need to ask him, have you done this? Why not? Try to see the reason. Go online, read it, try to change your code to make it happen. So vectorization, parallelization results. Let's see what we can gather from here. So for the for loop and the for loop vectorized, we see not quite an 8-fold increase, but 3, something like this. Is the effect of having your memory available or not available. Yeah. So from 45 milliseconds to 15 milliseconds, essentially for free. We added only one variable, max equals vector size, in the second function here. That makes max a local variable and provides the ability of the compiler to reason about over how many values we're actually iterating over. For each serial and for each parallel, so the second 2 lines in the debug console on the left here, they run at 11 milliseconds, so we get some kind of improvement for each, but not much. So why that is because the parallel execution, now it can use 8 threads to go through that, to go through all the data, but it doesn't mean that there's enough work for each of those iterations to offset the amount of work that is implicit, that we have no control over, that the compiler generated, that manages those threads or fires them up or closes them down. So it's just not enough work for it to be of any value. But if we do sorting, there might be enough work for the parallelization to show its effect. So if you want to sort these 50 million floats, then you can either do it in 300 milliseconds or in 92 by adding a single parameter. So from the bottom, the third function from the bottom for each parallel has an additional std execution parallel and then the rest is just the same as the above. Or sort as well. You know, the bottom function sort parallel versus sort serial. There's only a few characters worth of difference and a huge amount of performance difference. Okay, that's enough about vectorization and parallelization. What I wanted to convey is it can be extremely useful, but it requires you to have some kind of dialogue with the compiler. And that kind of dialogue and with the compiler is the topic of this next section. And we're going to have to go a little bit quicker because I don't want to take time off of you more than I said I would. So we're going to go through this also quickly. There are a few sections in this, in the few slides in the compiler section that requires maybe something from you as well, if you're interested in answering the questions. So the compiler has a profound impact on the performance of your program. It's in fact in between you and what you want to do and the machine, and it tries to satisfy both of you, and that's sometimes not very possible. And it can also be sometimes very unintuitive. Why are you not giving me these instructions? I made it very clear, and I'll show you an example of assembly code that is generated but kind of makes no sense, at least at face value. So it's useful to see things from the compiler's perspective and know what it's doing, what it's doing, and why. And there are tools that you can nudge it in the right direction. Briefly cover topics: inlining, aliasing, and pointer escape or pointer capture. So if you're not aware, inlining simply takes a function, normally a small function, and instead of generating assembly code that from some kind of outside function calls that and then returns back, instead it takes the content of this function you were about to call and just places all of it within the scope of the outside function. So there's no function calls, it just executes the commands that were supposed to be called in a different function, which is great because well, first of all, it's great for a variety of reasons, but it has some downsides. It can balloon your executable if that's something you're worried about. Maybe you're an embedded programmer and it has some strict limits on how much size you're allowed to have your binary. But in most cases, it's not. It also depends on how often you use these functions. Typically, inlining is done automatically, but you can turn it off, of course. I found it very useful, especially because the compilers are now clever enough to realize what is being used often and what might be inlined or not. You can suggest please inline, or you can suggest no inline. The please inline, it will hear you, but it might not do what you want. And no inline, it will hear you and listen to you, and it will not inline. So those are the rules. And I think this is true with all three major compilers, so MSVC, GCC, and Clang. So this is just an example of inlining. I'm going to go through this very quickly. On the left side, a non-inline function. If you look at the line 26 here, it calls my function sub. So it's simply a function that subtracts two numbers. It calls sub. It's the stack pointer. It does the actual subtraction and then goes back. This doesn't happen on the right side, where you can see in line 16, it performs the sub operation in line. So there's no function call. And there's function calls before to generate random numbers or whatever, but it does not. It never actually calls the function on line 1 on the right side. And this is good. Now the reason why I have all these rand, and I'm sure there are more elegant ways of doing this, is just to prevent the compiler from over-optimizing. I didn't want him to know what A and B are. Otherwise, he would just generate the result and hard code that into the code. So this is what I mean by fighting with the compiler. Sometimes it just over-optimizes for you because it doesn't understand that I have a presentation to make. All right, here's a question for the audience. I'm very curious if you guys can figure this out. It was certainly not intuitive for me when I first saw it. There's a little hint in the top left. It's about aliasing. So can anybody here in maybe in the next 2 minutes tell me what is wrong with this code? Assuming that it's correct, so it gives the right answer, but in terms of performance, what's wrong? We can also assume that when we're iterating, when we are providing an I that is always available, so these are raw pointers, you can overrun the buffers, but let's say that that never happens. In terms of the instructions that are generated or that have to be generated, there's something suboptimal here that's perhaps a little bit niche. Exactly. Yeah. So Michael Fitzenwalner, that's exactly right. So A, B, and C, or A and C, or A and B, they could be pointing to the same location. These are raw pointers. You could have C and A point to the same location in memory, or not even necessarily the same. They can overlap in a certain region. It's still a problem. The compiler, exactly, right? The compiler cannot prove that A, B, and C are independent. So let's see what the compiler then has to do. So in the first line of code, what it has to do is increment A by C. So what it's going to do is going to load C at I, but let's drop the index right now. It's going to load C, it's going to load A, it's going to perform a summation, and it's going to save and update the value at A. Then it has to load C again, which seems to be redundant because C should not change, right? It has to load C again, load B, perform summation, and store in B. Those are all the operations that the generated assembly has to do. So if you've noticed, we've actually loaded C twice. What our intention was here, and I'm sure if you just read the code, that's the intention is not to have C overlap with A, but if C and A point in the same location, then this increment, the C increment, changes because we changed A, therefore we've changed C through A. They point to the same location. Boom. Therefore, you have to reload C to know its current state so that you can use it then to update B. So it's kind of a tricky thing, something to be very aware of, and this is called pointer aliasing. You can prevent it. Well, I'm going to give you another example of the same thing. You can prevent it with a simple call. Same thing, right? So why would B in this code be reloaded over and over and over again? You would think that B does not change, but B and A here could also point to the same location. Yes, B is constant, but if you have the address of B, it doesn't matter if it's constant at all. So what this gives us is code that is probably 10 times slower than it could be, because remember, arithmetic operations are essentially free compared to the fetching of data. And here we are doing 10 fetches. Mov says, give me something from RAM and put it here. We're doing it over and over again. We don't actually need to. So B is being reloaded because the system cannot prove that A and B are actually not pointing to the exact same object in memory. But you can prevent that, right? So you can prevent that in one or two ways. If you just say int __ restrict A, and I think this is GCC syntax. I think just __ restrict is enough for Visual Studio. It says I want to use A and nobody else, no other parameter overlaps with me in any way. And then that additional load instruction for B will not occur, right? And not only that, so since it's not occurring anymore, the compiler is, with that issue out of the way, the compiler is able to apply more optimizations as well, like a vectorization that was just, that you can see on the right, it's actually vectorized the code now that it doesn't have to do these loads for no reason. Or if you don't like this restrict keyword, and I would use it, you can confuse yourself a bit more and still solve the problem by just changing the types, right? The same length type long in the bottom code listing here. At two types, long and constant, long and int, effectively will not alias. So that's just the rules of the compiler. So you don't have to use restrict, but then you're using long and int, and to me, the top code is much more clear. All right, another one. Again, quickly, there is in the code on the left side, first of all, I have to, this is not my code. I have to mention this is from a wonderful CPP con talk by Ofek Shilon, and in fact, the previous example as well, which he has graciously given permission for me to use here. I have not found a nicer code example to illustrate what pointer capture or pointer escape are. So I'm using his. So if you have time, check his CPPCon presentation. He does a better job of explaining this than me. But let's entertain the idea now, the code on the left side of the screen. So we have two functions, sumfunc and whatever. Sumfunc takes in a const reference to an int. The compiler doesn't have the access to the implementation of sumfunc or the implementation of whatever. And a function f is called that takes in an I int by value and a result by pointer to int, calls sumfunc. Again, the compiler still doesn't know what sumfunc is. It could be in a DLL, linked in later or whatever. And increments I, calls whatever, increments I, calls whatever, increments I, and calls whatever. Now, I here seems completely redundant. You're not doing anything with it, right? Why does it even exist in the assembly generated code? You could just take that I and say I equals I plus 3, or you can just remove together because it serves no purpose. And boom, you've simplified your code. But no, the compiler is not allowed to do that. And if you look at the assembly, it's actually incrementing it. How could that be? I'll give the answer because I really have to rush here. We don't have much more time. The reason is because sumfunc here takes in the I variable by a constant reference. So sumfunc has access to the pointer. It has access to the memory location where I is stored. And what it does with that, we have no idea. It could store it in some kind of global variable that controls the future control flow of the entire application. It could provide it to, by some other means, provide it to the whatever function. We don't have visibility in whatever either, right? So the pointer to a variable has escaped. So based on that, the compiler is not allowed to make any kind of judgment and is not allowed to remove the increments to I at all. I found that the example very interesting and again very counterintuitive if you just read the code. What's it doing? And maybe another case to actually look at the assembly output or look at the vectorization report, because the vectorization report might say things like I was not able to vectorize because clobbered by whatever I variable is not it cannot be removed, and that's what's preventing vectorization. So this is something called pointer capture or pointer escape, which is a slightly broader phenomenon that involves also returning of pointers back from the f function. So missed optimizations due to pointer escape, yeah. And you can also, there are directives that you can use to tell the compiler that sumfunc will absolutely not do anything with the const int that it takes in. So it will not escape. It will not let the address of I escape anywhere. So you're free to optimize away the I is in function f, or if you know it also for a fact, you can just turn the I here into a temporary, and you have a local copy, an address of that. You're fine with that, and you don't do anything with it in function f. Okay, let's go to the final part of the talk. We still have 20 minutes. That's more than enough, I think, to cover phase unwrapping and to maybe taking more questions if you're interested. So what I would like to do in this example is explain an algorithm that I've had some experience in, maybe tell you a bit about the background, what it does, how it does it, and then maybe we can go and try to apply some of the principles that we've seen especially in the first part of the talk, and maybe speed it up. So what is phase unwrapping? So phase unwrapping actually phase unwrapping can occur in many different scenarios. And the scenario in which I encountered phase unwrapping was for interferometry, right? So if you're trying to record or trying to measure the surface of a very, very, very tiny object, you would do this with a setup, with a physical setup like this, where on the right side you can see a ray of light bundle going down through a certain lens, reflecting partially reflecting off of a mirror. The second part of light goes through, reflects off the sample, reconnects, rebounds, and reconnects with the unmodified light, interferes with it, and goes back up. So this is a very accurate way of recording very small imperfections, very small features on, say, a physical sample of whatever you want to measure. This is nanoscale type measurement. And in processing these data, you could get images, well, during processing of your data pipeline, there could be many steps, but at a certain point, it's a very typical thing to lose some phase information. So the phase is what gives you the actual height of the object that you are trying to measure. And that phase information can get lost. So you might have all the phase information you have might be from -pi to pi, but your range, the actual range, might be from 0 to 7 or 8 pi. So multiples of 2 pi are lost, and you need to reconstruct them so that you can actually try to get the original signal back out, because the differences between the phase difference in the signal will give you an idea of the height of this object at every point. So if you look at the left image, what you're starting with, so in terms of input-output of the algorithm, what you're starting with is the blue line. So that's what we call a wrapped phase. And what you want to end up is the red line, and that's the unwrapped phase. So you need to figure out for each point, how many multiples of 2 pi do I need to add or subtract from this signal so that I get a smooth response. So it's of course idealized on the left side because there's always noise in any signal, and you need to come up with an algorithm that does this in presence of noise in a certain robust way. The left image is 1D, and the right image is what it would look like in 2D. So the first column and the right image is the wrapped phase, and the second one is the unwrapped. So for every point in the left two images, we would add a certain number of 2 pi, and such that the response on the right side is as smooth as possible. So that's the high level. That's the point of the high level algorithm. There's many solutions to this. There's plenty of literature that you can read about how to write algorithms. There's many algorithms written with certain performance, right? And typically they rely on some kind of heuristics, and so does the algorithm that we've chosen as well. So to sum up, to repeat again, need to find multiples of 2 pi such that when they are added to each of our pixels, so we're working with images, they produce in the end a smooth image. Plenty of publications, even GPU implementations as well. A perfect solution might not exist. So we chose one that seemed to give good performance, and it was already implemented for us. We didn't invent this from scratch. This is an OpenCV implementation, and it gives good results, but it's way too slow. So what can we do about that, and how much faster can we get? How much better can we get than OpenCV? So this slide is a little dense, but I will try to make it as clear as possible. It's actually not essential that you fully understand this slide. So how the algorithm works, big picture. First, we compute the pixel quality by some measure of quality. That's for every pixel, it's some function of its neighbors. For every pixel, it's a simple function, get quality of every pixel. Then for each edge of those pixels, you get the quality of the edges. And they are a simple function of the two pixels that join through that edge. So again, a very simple function. Then the unwrapping start. This was all preparation. So the time that goes into this preparation is very small compared to the actual unwrapping. So what we do is we go over all the edges in a semi-sorted fashion. So when we found out the reliability of all the edges, we classified all the edges into a large histogram where good, so high quality, what we call high quality edges are in the first bin, and the low quality edges are in the last bin. And we have some control over the size of these bins. And what we want to do is we want to start with the good ones, because good ones means, yeah, over this edge, not much has changed. You probably don't need to increase, plus 2 pi, minus 2 pi along that edge. So you start with the really good ones, and you start expanding this area. You're connecting to other edges that are also high quality. And if you find another, and you're creating a group of edges or a group of pixels, in that way, a region. And in another part of the image, these regions are also created. And so all regions start with a single pixel, and then they start expanding slowly. When they meet, even if it's a group of one pixel and another pixel, when they meet, the group that has a higher quality will consume the group that has a lower quality by telling the lower quality group to change its increment so that it fits with a higher quality properties of that group, and to change its group membership to the group that has just consumed it. So you can just imagine, and I wish I had time to make the animation of this. You can just imagine many small groups expanding, meeting at an edge, consuming one another, meeting at an edge, consuming, until there's one large group with the correct increment for every pixel. And this over time produces a smooth image in most cases, even in presence of noise. So larger groups tell smaller groups how to change increments. They consume them. And by the act of consuming all pixels of the smaller group, they have to change their increment per pixel and change their group membership per pixel. Okay. So big picture, what does a pixel need to know? Right? The pixel needs to know its phase value. So this is the, at the beginning, it's an unmodified phase value. In the end, it might end up plus 2 pi. It needs to know its index, whether it's valid or not, if you have some masks, like regions where you don't want to go into or whatever. Inverse reliability is just a technical term related to the paper, but it's actually a quality measure, an inverse of the quality measure that we want. We can just call it quality. Increment, it's how many times, what times 2 pi is a simple integer. Number of pixels in the group that this pixel belongs to, the group ID. So to which group does the current pixel belong to? It's also very important to know. And just the Boolean, is it a single pixel group or not? That's irrelevant. So what it really needs to know is, what's my phase, what's my quality, what is my current increment, and which group do I belong to as a pixel? So let's see how fast this thing can run. So I've also split out the sub phases of this algorithm, and I know that computing pixels reliability currently is 1 second. Edge reliability and generation of the histogram, it's almost 200 milliseconds, and the unwrapping takes 27 seconds. And this is on a not necessarily the latest machine, but a very fast Intel machine. Unfortunately, the algorithm is also written a single core, so yeah, 27 milliseconds for that. In total, the base solution, the one we're starting with before we start our optimization, is 28.5 seconds. So why is it so slow? And let's see what we can do about it. First, like the first thing I would do is just fire up the Microsoft Visual Studio Profiler and see what it tells me. So what can I see right off the bat? That's just one click, and this is the community version of Visual Studio, so you have this if you want. Or there's plenty of tools for this stuff anyway. So what I can first notice is in the top, there's a graph of how much my CPU is being used. From this, I can see that it's using only a single core. Fine. Okay. Now at the bottom, there's the hot path. It tells me which parts of my code are executed the most. So this is the loop. When I say hot loop, this is the part of the code that needs to have efficient instructions in it. And okay, fine. Let's see what else it can tell us. It says, all right, so in the next tab of the profiler, it can tell me that 21% of my time, so on the bottom left, 21% of my time is spent of total time is spent just iterating from k equals 0. So you see the red area to number of pixels, and the same thing on the bottom. So I'm having an if statement, and the if and the else of that both execute essentially the same code. If you see the for loop, the bright red parts, they are essentially the same code, and most of my time ends up there. 95% of my time, well, is in unwrapped histogram, but maybe 75, 80% is spent only doing those two loops. And this is fantastic because now I know, okay, it's not, I have a spot where 80% of my time lies. I mean, that's fantastic. I don't have to go anywhere else. I know if I shrink that down, I will get a 4 times speed up by itself. There's another thing here, and that's repeated code, which I would also refactor a little bit. So these two for loops, they should be extracted out somewhere else so that there's only one copy and it's more clear to read, etc., etc. But when I first saw this, I knew we're going to probably be able to speed this up because it's localized. It's easy to change this out. It should be easy. All right, so let's change this from array of structures, which I've just shown you. 1 second. So this is essentially array of structures. We have one pixel, and at the bottom, stud vector of pixels. That means that if I make a stud vector of this, I'm going to be addressing the increment, and I'm going to be addressing the face value of index 1, and I'm going to address those two fields in index 2 and those two fields in index 3, which means I'm throwing away most of my data during these iterations and throwing, therefore, most of my time away. And that's exactly what we're going to try. So we're going to go from arrays of structures into structures of arrays. Now I have one class called pixels, not pixel, and I'm going to just use standard C arrays for them, and I'm going to make sure that all of my increments, all of my group IDs are together, are contiguous. And I keep the interface of the class the same. All right, let's see what we get. Pixel reliability, so no other change has been applied. Pixel reliability goes down, edge reliability goes slightly up, histogram unwrapping goes from 27 seconds down to 10.7 seconds, and adding increments doesn't change at all. So we've gotten 2.5 times faster, just going SOA to AOS. But yeah, we can still do better than that. We can, for example, try to parallelize the update routine. So we still have these two for loops that have to go through all the pixels, but maybe we can chunk them up. And through, for example, MP, we can say, I want 8 threads, and I want the first thread to work on 1/8. At the same time, the second thread works on the other 1/8, etc., 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 and see what we get there. It's a one line of code kind of change. And that's the line, pragma OMP parallel 4. I've also extracted the critical for loop out of the code so that there's no repeated code, and just added pragma OMP parallel 4. And let's see what we get there. So firing up the profiler again, I see already that in terms of the utilization of the CPU, we're going way up. I know that it's running on actually 12 cores here, or 12 threads here. So I guess that's good. And we get, so SOA plus OpenMP to the right side, we get down to 4 seconds in total for the execution of the same algorithm. All we've done is change the internals of one struct and told OpenMP to do this in parallel. 7 times increase in total. But we can probably still do better than that. Now we're going to keep the structure of arrays approach because that seems to be working, but we're going to change the way that the algorithm works a little bit because I'm not happy about the way that the algorithm works at all. So the way that it currently works is whenever one group consumes another, there's a for loop, the critical for loop, that goes through every single pixel in the image, checks whether they are in the group that is about to be consumed, changes its increment and group membership to the new group, and then moves on to the next pixel. So in effect, you're iterating over the entire array, checking which group you're in. Are you about to be consumed? Yes. Change the internals, move on. So there's a lot of unnecessary work here, and that's just the iteration, checking whether of all the 5 million pixels, am I looking at the one that needs to be changed right now? It's enormously wasteful. So what we're going to do, and I'm not going to get into too much into the code. What we're going to do is we're going to have every pixel be aware of all the other pixels that are in the same group. I hope that makes sense. So every pixel is going to have a pointer to some container that will contain all its neighbors, essentially all its neighbors that are within the same group. So when we can imagine the starting condition of this program, every pixel is in its own group. They're a single pixel group in the beginning, and then they start coalescing. So if I know that pixel here indexes are the third row, pixel index 0 and 1, that 1 is about to be consumed by 0, what I simply do is I take a container that 0 points to, increment it by the contents of my index, and I move it in. I change my increment and group ID, and I move along. Then 2 and 3 have met. Index 2 and 3 have met. One of them is better. Say 3 has a higher reliability. 2 adds itself to a container that 3 is already pointing to. Remember, each group has only one container. All we change is the pointers to which container we currently belong to, and we move on. Now, the two groups meet at some point, and we increase the size of the container that was at index 0, and now it contains all the pixels that need to be adjusted because they are being consumed by some group. So now we no longer need to iterate through all the elements, all the pixels, to identify which group you're in, or which other pixels are in this group. Now you have that list immediately there. So any pixel that gets joined will have a list of all its neighbors, and that's the list you need to list. That's the container you need to iterate through. So to me, it's a basic algorithmic improvement, which should have been already done on the side of the OpenCV developers. That should increase performance by a lot, because imagine you have 50,000 groups, and you have to go through 50 million elements to investigate in which group you are, and if you are in this one, change. Now, any pixel you encounter has a pointer to all its other members, all its neighbors, and everything is quicker. However, so what can we use? Which container do we use to keep track of these group memberships? We know that we need a container that can be iterated over fast, and we know that we need a container that can be spliced fast. So, for example, a list you can splice together list information very quickly. Say one list that has 50,000 members and another list that has 50,000 members. You can just repoint. The last member of the previous list points to the first of the second one, and that's I think done through stud list splice or join, and it costs 0 time to do this. But lists takes a lot of time to iterate over, right? Because you are doing, by definition, you're doing pointer chasing when iterating through a list. So it fulfills one of our conditions, which means being splice fast, but not iterate over fast. So iterating over to whatever, update the increments, right? So lists I tried, and they were pretty slow. Luckily now, since C++11 and the introduction of iterators, you can play around with which container I want to use for this very, very easily, because the syntax is the same for all of them. The iterator mechanism will just do all the work for you. So another option is vectors. So if I want to iterate over vectors, there's nothing faster, because you are really iterating across contiguous elements that are cached. But splicing of one vector onto another is expensive. You have to allocate another a much larger vector and put the two together. It turns out the stud deck is something in between, but through testing, I just found that iterators are by far much more faster than lists and slightly faster than decks. So I stayed with vectors, and broke one of my rules, and that's no allocating in a hot loop. But in this case, we've gotten so much speed up that I didn't care anymore. So in total, the total speed up of our approach, so structure of arrays plus changing the algorithm slightly, simplifying it, and using vectorization. Now vectorization is possible, remember, because we can do 8 wide increments, and we can do 8 wide group changes because our data is contiguous now. We got to a speed up that's 80 times faster than base. So and that's for a relatively short amount of invested time. So going from 28 seconds to 330 milliseconds opens doors, right? So it makes this code usable in different, for different applications. Okay, so I'm just about to run out of time. It's 11:30. I think it's time to maybe unzoom a little bit and maybe comment high level on optimization. So again, if I was tasked to do something, or if I was evaluating whether optimization is necessary, should be done or not, that's a really important question to ask. Is optimization even needed? It's much more cheap to buy. That's cheaper to buy a slightly more expensive computer than to, in most cases, pay for engineering time 1, 2, 3 days, or 5 days, or 1 month. So there's not many companies that are willing to do this unless they have to. For example, Meta, or Facebook, Meta, they were so focused on optimization, they developed their own compilers and programming languages to make Facebook run faster, or some kind of special databases, just so that every person that's looking at Facebook, if they have to wait half a second longer, it's no longer attractive. So is optimization needed is the first question, is the most important question to answer. Then another tenet of optimization is never to optimize prematurely. It's a very easy trap to fall down. I've had it happen many times. When you're starting to write something, don't write it in an optimal way. What I do is I just write a prototype in MATLAB or in Python, then a silly thing in C++. When I get the correct solution, and only when I get a correct solution, then we start playing with, should we optimize? Should we use a GPU? Or do we have an FPGA? Or do we do this on the CPU, etc., etc.? But it's immensely important never to try to do this stuff right off the bat. So even now, you have a class person, I would go, name, last name, phone number. I don't care about the structure of arrays yet. It's for later. Don't over optimize as well. It's kind of addictive. Once you can see that this thing can go faster, you want to do it more and more and more. But remember the 80-20 rule, and just keep a cool head about it. Probably your user won't care if you shave off 7 milliseconds off the solution time of something that's that he's fine having run for 1 second. Starting from the low-hanging fruit, so pretty much in the order of the presentation: data structures, vectorization, and then looking at the compiler. And then asking yourself, where's my basic profiler? Yeah, I'm sure you have access to it. There's plenty of them. Can I make a mock test setup? Is the code ready for it? Do I have a basic timer class? You can use standard C++ and make a timer class. It's 50 lines of code. It will give you a lot of information for in a very short amount of time. And then do I know that a necessary work is being done? And of course, you got to know something about the hardware. That's the common sense part of this talk. Don't expect performance if you're dealing with networking, or if you're dealing with the hard drive, or if you're unoptimally accessing your data structures. And most importantly, and you'll find this everywhere, always measure, measure, measure. The baseline has to be measured. Time of each function, when you get serious about it, has to be measured. Profilers are fantastic for this, and they're free and accessible for any platform. Okay, thank you. That's it for my talk. I think we're just on time. These are the links. I know this is being recorded. I don't know if it's also being shared in PDF or PPT form, but you can actually find all of these just by Googling them. These are excellent resources that I've used to create the talk from. So yeah, thank you very much. I hope it was as interesting to you to listen as it was for me to prepare it. And I'm happy that many people find this kind of stuff interesting. If you have any questions, I'm still here. Otherwise, thank you very much for attending. Especially you, Gert. Gert-Jan facilitated everything, and of course, EuroCC Belgium. Without them, this would not be happening. For me, I think it's a great opportunity and to network and to see what they're all about and to present something I'm passionate about.
Okay, Vukasin, thank you very much for this very nice presentation. I'm pretty sure that the participants really enjoyed it. So, as has been mentioned, there is a recording of this session. If you want access to that, just drop me an email and I'll make a link of it available. Due to GDPR reasons, this will not be public. It will be on YouTube, but as unlisted. Again, if you need a certificate, also drop me an email. It's not going to be automatic for staff members or students of Belgian universities. So you would really have to ask me. If there are any further questions to Vukasin, feel free to put them in the chat.
Or you can always contact me. So this is me. I'm available normally on LinkedIn. I answer messages. If you're interested, please. I'm always happy to network, especially about topics like this. Geert-Jan, are you aware of other presentations as part of VSC or EuroCC that will be happening in the near future?
Well, our training season is more or less over for this academic year. But of course, we have a cycle of presentations and trainings that are of interest. So, for instance, if you're interested in tuning vectorization, then the parallel programming with OpenMP might be for you, because that's a very nice way of not having to use compiler-specific intrinsics and
Yeah.
direct the compiler to do proper vectorization anyway. Also, of course, the whole OpenMP thing can be of interest. There is also a presentation on code optimization, typically a training on code optimization that covers a lot. Well, there is overlap with what you presented, but it's not specific to C++. It's more, let's say, keeping to the level of Fortran and C, rather than delving into C++ specifics. Apart from that, there's the usual stuff about Fortran programming, C++ programming, and so on. So, but that will be for next academic year.
Okay. Okay. And did you find this talk to be too much in detail? Probably not, but as I've said before, any of these topics can go more in detail. For example, you could show how to use a profiler or which profilers exist or how is it different on Linux. I mean, you can really go in depth, whichever. So do you think that going in depth more in these topics would be less attractive for people? Or what would be a good talk to give?
Yeah, it's frankly it's difficult to say. So an in-depth talk might be very interesting, but then it should be very clear from what the expectations are towards participants.
Yes.
So expectation management is quite important then. That's something I very often notice in trainings, that people have some expectations, and that it is a little. If you want the recordings, please just drop me an email. That would be the best thing to do. So, with respect to no, please send me an email, because this chat is not recorded. So if you don't send me an email, you won't get the recording. Um, so it would definitely be interesting to do some in-depth sessions about more specific topics. But then, of course, communication has to be quite well managed.
Clear. Yeah, yeah. And you would expect fewer people to join?
It depends.
And does this actually matter? That's maybe a better question for VSC, for EuroCC. Is it more beneficial for them or for us to create sessions that are less in depth but are more populated, or not?
Well, it depends a little bit on the vision. So
Yeah.
back in the praise days, praise really preferred in-depth courses. EuroCC, to my knowledge, doesn't really have clear ideas on that yet. So basically, we kind of do whatever we want. That's basically the bottom line. If you did that for praise, you would get into trouble getting a training session approved. So things were different. I don't know.
Yeah. Okay.
But I think we can see what's interesting, and we can discuss this perhaps at some point, and see how we can come up with some interesting ideas there.
What do you think about? I mean, if we keep it at the same level as I just presented, but I can imagine doing a more general training session, a hands-on training session, where I would do it on site or maybe even remotely again, and we pose a problem or provide some kind of basic solution and ask people to fill in the blanks and try to see, provide a timer class, try to see what they can do on their own. 5 or 6 principles, and have people the freedom, half an hour, implement what you have. I think doing this yourself after somebody has explained it and trying and fighting with it until you
Absolutely.
get something better is very good. For training, it's
Absolutely.
excellent.
But we might have to, or we might want to think about a format. I have some ideas about this. So, for instance, because I would prefer at least hybrid. The reason is that certainly in Belgium, getting people to travel is hard. So
Yeah.
typically, if you can do something hybrid or online, you will have better participation. So what could be an option, for instance, is to indeed do this, but make part of the experimentation, part of the hands-on, asynchronous. So basically something like, okay, there is a presentation that shows some concepts. Then there is a presentation of the hands-on exercises to do. People indeed get time to do them, but that might be something like over a day or something like that.
Mm-hmm.
And then the next day you continue.
Okay, I
With
see.
something like that might be an option to think about. I've never tried this, so it would be a
It
bit
should
of an
be. It should
experiment.
be.
I also don't know of any example of this, but it might be an interesting format.
I was thinking about the same thing. I mean, you could. Well, let me restart. There is another technical issue, which is the following. So if we are disconnected, if everybody is sitting at home, then we don't have access to the computational resources of the VSC. So people can't log in. Excuse me. People can't log in and count on the fact that they're all in the same compiler, right? And
That is true.
I cannot easily distribute code like a class, a timing
Mhm.
code or something like that. But we can partially work around that by having everybody log into Compiler Explorer. There are online resources where you're completely free
Mhm.
to write code from scratch, correct C++
Yes.
code with as long as you want, and it'll do the timing for you. So that's a resource. So programming online should be fine. Yeah, should be fine.
Mhm.
Sharing the results is the tricky part. So I can't have like a
Yes.
list of people that this is the timing for each of them, which would be possible if we were on site. But yeah, such is life. Eh?
Yeah, and
So
also the problem is that having using the VSC as a resource requires accounts,
yes,
and that is easy for Belgian participants. That is, to put it mildly, a lot more difficult for foreign participants.
I see. Yeah, 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 yeah.
So, what is an option? But then again, comparing results might not be obvious. is making sure that there are Amazon virtual machines. That's something I already did for training. So that is possible, but of course there is a price tag attached to that.
Yeah, that's not free. Well, I'm sure we can figure out a way to I'm sure we can figure out a way to do this without having to resort
Mhm.
to anything that's paid. I just need to think it through. Anyway, it's not in the short
Mhm.
term. I would love to do this eventually, as soon as I get
Mhm.
the time, because yeah,
Mhm.
I have a job just like everybody else. I do this on the
Mhm.
side, but I'm sure I'm thinking about it constantly. There has to be a format, and I will find it that works well for a large number of participants and coding and online. I'm sure it exists.
Okay, there
Okay.
is a remark in the chat about this, but that will probably be but that is most likely using NVIDIA
Python.
resources.
Yeah,
So I've attended several of their trainings, and most likely this is through DLI.
what is DLI?
That is the digital something of NVIDIA, digital school for whatever thing.
Ah,
So that's typically for GPU programming, and you can use this, but then you have to be an NVIDIA certified instructor,
okay. Well,
which is not necessarily obvious, because that takes a while, and that is also something that you have to redo quite often, because you can only be an NVIDIA certified instructor for essentially their training material.
I see.
And if they change it, you have to take an exam, etc., etc. So I've looked into that. It's feasible, but it's not obvious.
Okay. Okay. That's good to know. Yes, programming, GPU history.
Okay, let's see.
I really wonder how many visitors, how many attendees the Praise GPU class would get. I find that it's probably not a lot.
Which one do you mean?
If you were the first one, the GPU programming, the the amount of people that are interested in learning CUDA nowadays is not very high.
No, true. So interest is shifting a little bit to using libraries that run on GPUs. And indeed, CUDA is somewhat getting out of favor due to AMD, whatever they tell about automatic hit conversion and so on. Interest in CUDA is indeed a little bit waning. On the other hand, what is interesting is doing OpenMP on GPUs or
Oh,
OpenACC on GPUs. That is interesting.
I don't know
That
how
is
to do that.
something I'm currently looking actively into.
Okay, I'd be curious to hear about that.
Mhm.
Maybe I mean I'm going to take a look at the trainings in the future. I think
Mhm.
my company wouldn't have a problem of me coming over and hearing a lecture or doing it online. Um,
Mhm.
very useful stuff. I was a little bit surprised at VSC that not more people. I've told you this many times that not more people are participating in this. It's free value
Yes, of
with
course.
experienced
It is.
people. And you could go online and pay for this kind of stuff. But yeah,
Yeah,
crazy.
exactly. That is a little bit disconcerting. Yeah, um, I can't really tell you why that's the case. So typically, indeed, we don't have that many participants. It's okay. I mean, it's more than enough to keep the thing going. But yeah, one of the things that might not help is that it's free,
Ah,
because in perception, free sometimes equals low quality.
I haven't thought of that. Yeah. Well,
So,
do,
for
do, do,
instance, if nowadays you want to follow a course at HLRS, then basically you will pay 300 euros for a 3-day course. It's not a huge amount of money, but it puts some value on it.
It's very very strange. I mean, I agree with it, of course. This is the reality, but just never think that way.
Yeah, it's something that I've in the past, of course, Praise training courses were for free because Praise was subsidizing them. It was, well, at least in part paying for them. But Praise, nobody knows what is going to happen.
Yeah.
Yeah, no shows is also indeed a problem.
Yeah.
Yeah, and indeed, dealing with the financial things is, for us, it's also very difficult. For instance, for the VIC, it's basically impossible because we're not a legal entity. So how can we do financial transactions? It's just not possible legally. We can't do that.
Even
So
if it was, even if it was possible legally to do that, just administratively, it's a lot of work.
yeah, it's a lot of work. I mean, I know the situation at HLRS, and it is maybe similar at Jülich, but the problem is essentially that indeed at HLRS there is a half-time person just managing the stuff. So
Yeah.
all the payments, all the registrations, and so on. So yeah.
Maybe best to keep it simple.
Mhm.
Marketing, I don't know if you have people that are putting up posters or informing, let's say, computer engineering building, and having other professors disseminate this information. If I was to look around at those TVs that are placed in one of those buildings and, oh, look, there's a training
Mhm.
session for that, I'd be much more inclined to join.
True.
So a marketing thing, perhaps, and I'm no expert in this, but common sense,
Yeah.
posters.
We actually have been looking at this. So basically, of course, from the perspective of VSC, we are mostly interested in potential users. And of course, computer science people are, to a very low degree, potential users.
To a low
So that
degree.
means we would have to recruit in, let's say, chemistry, physics, etc., etc. And then you're talking about going to many different buildings to distribute posters, because I'm not so sure that there is an automatic or let's say an organized thing to do that, and that at all the universities.
Yeah.
So it's not that easy. Also, we tried at some point to actually get our promotional material onto those screens which you mentioned, and that was also interesting.
Huh. Wow. Yeah. Interesting.
Oh yeah,
Yeah.
okay, that's interesting to know. Yes, yeah,
Wait.
yeah,
I'm sorry, Het. I will have to leave at 12.
no problem.
Uh, Again, thank you very much. Yeah.
My
It would
pleasure.
not have happened.
Thank you for doing this. It was very nice to have you. And
My
we'll
pleasure.
definitely do a repeat in some format of this in future, next academic year somewhere. So if you're up to it, if you want to participate again, that would be
Absolutely.
very nice.
Absolutely. Of course. No. Anytime. I mean, for me, it's also free value. I like talking about this
Mhm.
one, but I'm also
Mhm.
networking.
Yeah,
So it's
absolutely.
good. It's good for everyone. I'm happy that my company allowed me 5 or 6 days to prepare the talk. I first gave it at my
Mhm.
company, and then now I can give it elsewhere, provided I reference them, etc. It's everybody wins in the end.
Mm.
Okay, thank you. I hope to hear from
All
you
right.
guys soon. I'll certainly be around. Um, and yeah, see you soon. I hope in one of the trainings as well.
Okay.
Thanks, Gert. Bye, everyone. Thanks
Yeah.
for joining.
See you
Bye
later.
bye.